Right now, inside your computer or your phone, there is a frantic, invisible relay race happening at the speed of electricity. Millions of times per second, tiny pulses of energy are sprinting back and forth between your processor and a slender stick of hardware that most people take for granted. We call it RAM, or Random Access Memory. But specifically, we are talking about DDR. Without this specific technology, the modern digital world would grind to a stuttering, frustrating halt. Most people know that more RAM is better, but very few understand the generational war that has been fought over the last 2 decades to make your web browser open half a second faster, or your favorite game run at a smooth 60 frames per second. Today, we are going to deconstruct the history, the physics, and the sheer engineering genius behind every generation of DDR memory, from the blocky, slow beginnings of the late 90s to the blistering, high-voltage efficiency of the hardware coming out next year. We are looking at the evolution of digital speed. If you've ever wondered why you can't just stick a new piece of memory into an old motherboard, or what all those confusing numbers like CAC latency actually mean for your daily life, you are in the right place. Let's dive into the silicon abyss. To understand where we are going, we have to understand the fundamental bottleneck that almost destroyed the computer industry in the 90s. Back then, processors were getting faster and faster, but the memory was lagging behind. Imagine having a world-class chef who can cook a meal in 30 seconds, but the waiter taking the food to the table can only walk at 1 mile per hour. That waiter is the memory. Before DDR, we had something called SDRAM, or Synchronous Dynamic Random Access Memory. It was synchronous because it waited for a clock signal from the motherboard to move data, but there was a massive limitation. It only moved data once per clock cycle, on what we call the rising edge. It was inefficient. The industry was desperate for a way to move more data without just cranking up the clock speed, which causes heat and stability issues. Then came the breakthrough, double data rate, or DDR. The double in the name is the literal secret sauce. Instead of just sending data on that rising edge of the clock signal, engineers figured out how to send data on the falling edge as well. It was like taking a one-way street and suddenly allowing traffic to flow in both directions simultaneously. This effectively doubled the bandwidth without changing the clock frequency. The first generation of DDR hit the market around the turn of the millennium, and it changed everything. Suddenly, those high-end Pentium and Athlon processors had enough food to keep them busy. DDR1, as we now call it, operated at voltages that would seem massive today, usually around 2.5 volts. It was the Wild West of memory, with clock speed starting at just 100 megahertz but providing a throughput that left the old SDRAM in the dust. But as with all things in technology, as soon as we solved one problem, we created a new one. Processors continued their relentless march forward, and by the mid-2000s, DDR1 was becoming the new bottleneck. The industry needed more speed, but they also needed more efficiency. Enter DDR2. If DDR1 was a two-lane highway, DDR2 was a complete redesign of the interchanges. The big innovation here was the 4-bit prefetch. Without getting too bogged down in the weeds, this allowed the internal clock of the memory chips to run at half the speed of the external data bus. This meant we could achieve much higher external speeds without the internal silicon melting from the effort. DDR2 also lowered the operating voltage to 1.8 volts. This might not sound like much, but when you have millions of these things firing constantly in data centers across the globe, that reduction in power consumption and heat was a game changer. This was the era of the Core 2 Duo, the time when 4 gigabytes of RAM felt like an infinite amount of space. However, the architecture of DDR2 eventually hit a wall. To go faster, we needed to change the way the memory communicated with the processor again. Around 2007, DDR3 arrived on the scene. This generation pushed the prefetch from 4 bits to 8 bits, further decoupling the internal speeds from the lightning-fast external data transfers. DDR3 was a massive success, staying relevant for a nearly unprecedented amount of time. It dropped the voltage again, down to 1.5 volts, and later, a low-voltage version called DDR3L hit 1.35 volts. This was the era of the modern laptop as we know it. Thin, light, and capable of lasting several hours on a single charge. DDR3 allowed for much higher capacities on a single stick of RAM, moving us from the era of megabytes into the era of 16 and 32 gigabyte consumer machines. It was reliable, it was fast, and it defined the computing experience for almost a decade. But then came the era of big data and high-resolution gaming. The move from DDR3 to DDR4 around 2014 wasn't just about speed. It was about the fundamental way memory modules were structured. DDR4 introduced a bank group architecture. Imagine a library where instead of one person looking for a book, you have 4 different teams working in 4 different sections of the building at once. This drastically reduced the time the processor had to wait for the memory to find the specific bit of information it needed. DDR4 also brought the voltage down to 1.2 volts. For gamers and professional video editors, DDR4 was a revelation. We saw speeds climb from the base of 2133 MHz up to over 4000 MHz in high-end enthusiast kits. Capacity also exploded. Suddenly, putting 64 or even 128 gigabytes of RAM into a home workstation wasn't just a dream. It was something you could actually buy at a local store. Now, we find ourselves in the early years of the DDR5 era. This isn't just an evolution. It's a radical departure from everything that came before. In all previous generations, the motherboard was responsible for managing the power going to the RAM. With DDR5, that power management circuitry moved onto the RAM stick itself. This allows for much finer control over the voltage, which is now down to a mere 1.1 volts. But the biggest change is the dual-channel nature of a single stick. In the past, you needed 2 sticks of RAM to run in dual-channel mode to get maximum performance. A single stick of DDR5 actually has 2 independent 32-bit channels on it. It's like having 2 separate memory sticks fused into one. DDR5 also introduces something called on-die ECC, or error correction code. As memory cells get smaller and smaller, they become more prone to bit flips, random errors caused by heat or cosmic rays. DDR5 can find and fix these errors inside the chip itself, leading to a level of stability that was previously only available in expensive server hardware. We are seeing starting speeds of 4800 MHz, with projections of hitting over 8000 MHz in the near future. It is a staggering leap in raw bandwidth. But why can't you just mix and match these generations? If you look at a stick of RAM from each era, you'll notice a little notch in the bottom connector. That notch moved with every generation. This is a physical guardrail to prevent you from accidentally frying your hardware. Each generation of DDR uses different voltages and different signaling protocols. If you manage to force a DDR5 stick into a DDR4 slot, the physical and electrical mismatch would likely result in a very expensive puff of smoke. This is why every major memory upgrade usually requires a new motherboard and often a new processor. It's a synchronized dance between the 3 most important components of your computer. Let's talk about latency, because this is the part that confuses most people. You'll often see a series of numbers on a RAM package, like CL16 or CL40. This stands for cache latency, which is essentially the initial delay before the memory starts sending data. Think of it like a conversation. Bandwidth is how many words you can say per second. Latency is the split second of silence after someone asks you a question before you start answering. In many cases, having lower latency is just as important as having high bandwidth, especially for tasks like gaming, where the processor is constantly asking for small pieces of data right now. As bandwidth has gone up with each generation, latencies have also technically increased. But because the underlying clock speeds are so much higher, the actual time in nanoseconds has remained relatively consistent or has even improved. It's a delicate balancing act that engineers have to perform with every new design. But DDR isn't just for your desktop PC. We have specialized versions like LPDDR or low-power DDR. This is what lives inside your smartphone and your ultra-portable tablets. LPDDR is designed for a world where every milliamp of battery life matters. It has deep sleep modes that allow it to consume almost zero power when you aren't looking at your screen, but it can wake up instantly when you touch an icon. We are currently seeing the rise of LPDDR5X, which provides desktop-class speeds in a package that fits inside a device that sits in your pocket. Without the work done on LPDDR, your high-resolution phone screen would drain its battery in 20 minutes. There is also GDDR, or Graphics DDR. This is the high-octane sibling of standard RAM, and it lives exclusively on your graphics card. While standard DDR is built for low latency, answering the processor's questions quickly, GDDR is built for massive throughput. Your graphics card needs to move millions of pixels and textures every single frame. GDDR6X, the current king of the hill, uses a technology called PAM4 signaling to move twice as much data in the same amount of time as standard signaling. It runs hot, it consumes a lot of power, and it's incredibly expensive, but it's the reason modern games can look so photorealistic. It's a specialized tool for a very specific job. As we look toward the future, the industry is already whispering about DDR6. We are reaching the physical limits of how small we can make these memory cells without them becoming unstable. The next frontiers are things like stacked memory, or HBM, high bandwidth memory, where the memory is placed directly on top of the processor, instead of being inches away on a motherboard. This reduces the time it takes for electrical signals to travel, which is becoming a significant factor as we push toward speeds where the speed of light itself is a limitation. We are also seeing research into non-volatile RAM, memory that doesn't disappear when you turn the power off. Imagine a computer that turns on and is exactly where you left it in a fraction of a second, with no boot-up time at all. What does all of this mean for you, the user? It means that we are living through a quiet revolution. Every time you open a high-resolution image, every time you join a video call with 20 people, and every time you explore a massive open-world game, you are benefiting from 25 years of intense engineering competition. The move from DDR1 to DDR5 represents an increase in bandwidth of over 50 times, and a reduction in power per bit that is even more dramatic. It is one of the most successful examples of long-term technical cooperation in human history. But there's a catch. As memory gets faster and more complex, it also becomes more sensitive. Modern RAM is susceptible to things like electromagnetic interference and heat soak. This is why high-end RAM sticks often come with elaborate metal heat sinks and even RGB lighting. While the lighting is mostly for aesthetics, the heat sinks are becoming a necessity. At the speeds DDR5 operates, even a small amount of heat can cause the memory to throttle or slow down to protect itself. This makes your computer's cooling system more important than ever. We also have to consider the role of the memory controller. This is a tiny piece of circuitry inside your processor that acts as the traffic cop for all this data. Not every processor can handle the fastest RAM on the market. If you buy a kit of 800 MHz RAM and pair it with a budget processor, that memory controller might struggle to keep up, leading to crashes or blue screens. This is why stability testing has become an art form for computer enthusiasts. It's about finding the sweet spot where the memory is running at its maximum potential without overwhelming the rest of the system. Let's touch on multi-channel memory again, because this is the single biggest mistake people make when building a computer. Most modern motherboards have 4 slots for RAM. If you only buy 1 stick of RAM, you are effectively cutting your available bandwidth in half. It's like having a V8 engine, but only letting it use 4 of its cylinders. Always buy your RAM in pairs. This allows the memory controller to access both sticks simultaneously, doubling the amount of data that can be moved. Even if you have the fastest DDR5 on the planet, a single stick will often perform worse than a slower pair of DDR4 sticks running in dual-channel mode. It is the fundamental rule of memory architecture. 2 is always better than 1. Then there is the concept of overclocking and XMP or expo profiles. When you buy a stick of RAM rated for 5200 MHz, it doesn't actually run at that speed out of the box. By default, it runs at a safe, industry-standard speed, which is usually much lower. To get the speed you paid for, you have to go into your computer's BIOS and enable a profile that tells the motherboard exactly what voltage and what timings to use. This is technically a form of factory-supported overclocking. For the average user, this is the most important step in setting up a new machine, yet it's the one most often skipped. You might be leaving 20% of your computer's performance on the table simply because you didn't click one button in a menu. As we go deeper into the technical side, we have to talk about subtimings. Beyond the CAS latency we talked about, there are dozens of other numbers that define how the memory operates. These control things like how long the memory has to wait after writing data before it can read it again, or how often the cells need to be refreshed with a burst of electricity. Memory is volatile, meaning it forgets everything if it loses power. But even when the power is on, the tiny capacitors inside the RAM chip slowly leak their charge. Every few milliseconds, the entire memory has to be refreshed to prevent data loss. As memory gets faster, these refresh cycles become more complex and can actually start to interfere with performance. Engineers are constantly looking for ways to make this process more efficient so that the memory can spend more time moving your data and less time just trying to remember it. Have you ever wondered why RAM is so expensive one year and so cheap the next? This is because the world of DDR is a commodity market. There are only a few companies in the entire world that actually manufacture the silicon chips. Samsung, SK Hynix, and Micron are the big three. Everyone else, like Corsair or G.Skill, buys those chips and puts them onto their own circuit boards with their own heat sinks. Because the manufacturing process is so complex and requires multi-billion-dollar factories, any slight disruption, a power outage, a shortage of raw materials, or a sudden surge in demand for smartphones can cause prices to skyrocket. It is a fragile, high-stakes global supply chain that keeps your computer running. We should also mention the form factors. Most people are familiar with DIMMs, the long sticks that go into desktop computers. But laptops use SODIMMs, which are much shorter. Recently, a new standard called CAM has been introduced to replace SODIMMs in high-end laptops. As we push for thinner devices and faster speeds, the traditional slot for RAM is becoming a problem. The long traces or wires on the motherboard act like tiny antennas, picking up interference. CAM moves the memory closer to the processor and uses a more direct connection, which might be the only way to get DDR6 and beyond into portable devices. It's another example of how the physical shape of our technology has to change to keep up with the demands of the code we run. The history of DDR is a history of overcoming physical limitations. We fought through the half-speed internal clocks of DDR2, the power hungriness of DDR1, and the signal noise of DDR4. Every generation is a victory of human logic over the chaotic nature of the physical world. It's about taking billions of tiny buckets of electricity and making them move in perfect harmony, billions of times every second, without losing a single drop of information. When you think about it like that, a stick of RAM isn't just a component. It's a miracle of modern manufacturing. In the world of servers and data centers, DDR takes on even more importance. They use something called registered or buffered memory. Imagine a crowded room where everyone is shouting at one person. That one person, the memory controller, will eventually get overwhelmed. Buffered memory adds a middleman that collects all the requests and organizes them into a neat line before passing them on. This allows servers to handle hundreds of gigabytes or even terabytes of RAM on a single motherboard. It is slower and more expensive than consumer RAM, but it allows for the massive scale of the cloud services we use every day. Without the specialized server versions of DDR, platforms like YouTube or Netflix simply couldn't function. As we move toward the end of our journey, let's reflect on the incredible rate of change. If you could take a modern stick of DDR5 back to 1995, it would have more bandwidth than the entire global internet did at that time. It is a level of progress that is hard for the human brain to truly grasp. We have moved from treating memory as a storage closet where we keep a few files, to treating it as a high-speed workspace where the entire digital environment lives in real time. What's next for DDR? We are seeing the rise of CXL, Compute Express Link. This is a new technology that allows memory to be shared between different computers over a high-speed network. Imagine a data center where the RAM isn't stuck inside one box, but lives in a pool that any computer can draw from as it needs it. This would solve the problem of stranded memory, where one computer has way too much RAM and another doesn't have enough. It is a radical reimagining of the very architecture of a computer, moving us away from boxes and toward a liquid model of computing power. The secret to DDR's success has always been its ability to adapt. While other technologies have come and gone, the fundamental idea of double data rate has proven to be incredibly resilient. It has survived the move from massive desktop towers to smartphones, and now into the world of artificial intelligence and high-performance computing. Each generation has been a response to the specific needs of the time, and each has pushed the boundaries of what is possible with silicon and electricity. Every time you hit save, every time you load a web page, and every time you start a game, you are witnessing the culmination of millions of man-hours of research. Next time you see those slender sticks of hardware through the glass side panel of a computer, I hope you see them for what they really are: the fastest, most precise, and most essential relay race in the world. The silicon abyss is deep, and the speeds are only going to get faster. Stay updated on your hardware, keep your drivers current, and remember to always run in dual channel. The future of memory is coming, and it's going to be faster than any of us can imagine. Technology often feels like it's just there, but it's important to remember the people who spent their careers figuring out how to shave a few picoseconds off a signal delay, or how to make a capacitor hold a charge for just a little bit longer. DDR memory is a testament to the power of incremental progress. It's not about one single eureka moment, but about thousands of small improvements that add up to a revolution. As we push toward DDR6 and the limits of the physical world, the story of memory is far from over. It's just getting started. Thank you for taking this deep dive into the architecture of speed with me. Your system is only as fast as its memory, so respect your RAM, and it will keep your digital world moving at the speed of thought.